Omaha.
What's that?
Where are we going to Omaha?
So we're going to both actually.
Oh, yeah?
Yeah. So Omaha, the Omaha trip, Lincoln trip to the zoo for the STEM club will be the 26th.
It's the same name you gave us before, right?
Yeah.
Okay, right, because the thing was
So it's April 26th we'll leave, and then we'll be gone 26th and 27th. Come back the evening of the 27th. And I've applied to do the tour at the museum, and we are registered at UNL to go to the thing there. We've got hotel rooms, we've got a van to travel in, we're good to go. So yeah, we're in good shape as far as that goes.
Road trip.
Road trip.
Oh, shoot, the road trip with Scott.
Riding along in my automobile. Gotta have some good music, man. Me and my baby behind the wheel.
I'll keep an eye on back for you.
Gotta have good road trip music, man.
Yeah.
50s music works really well. All right, so, what's that country song? Life is a highway.
Yep.
I'm gonna ride it all night. That's a good driving song. Beach Boys are really good driving songs. Anyway, okay, so Johnny Cash, some Johnny Cash I can't handle. It's just too much.
Yeah.
But there's some that really rocks. So anyway, yeah. So 26th, 27th is when that's happening. So that's that. Also coming up, we have on the 10th our trip to Ogallala. I'm gonna be here with a van, probably around 7 a.m. and packing up stuff to go to Ogallala. We're supposed to be there around 8 o'clock. So we're gonna pack some.
We'll be back by like noon or 1, right?
Yeah, we should be back by 1 or 2.
I'll probably just meet you up
Do that. So that's our trip to Ogallala. So we won't have class on the 10th. We will probably just do class on the 11th and not have a lab that week. There's just not a lot of labs we can do with this stuff. I mean, we could have measured the speed of light this week for this lab, but we've already done the speed of light. You can't really do relativity experiments very easily in a laboratory classroom like this. You know, they just barely did relativity experiments in laboratories that were 2 miles long. You know, they were able to do those. Those laboratories had 60,000 mega electron volts of energy. And, it's just situations we can't reproduce in the classroom.
And if we want to do that for a couple of weeks, I'm okay with it.
Yeah, we from now on we really won't have a lot of labs to do. We will do a radiation lab a little bit later when we get into medical applications of radiation. So we're going to radiate something, make something radioactive in here. Maybe a student. We'll choose a student and make them radioactive. Who wants superpowers, man?
Dagger? I'll take Wait, we gotta get him bit by a spider first.
No, this is going to be radiation.
I just want to glow in the dark. That's all.
Yeah.
So we need to pour that stuff out of one of them sticks when you first. All right, now let's radiate.
So anyway, that's what we got going. Got a test this week. If you can't get the test done this week, then I can move it to next week a little bit as well. So then we'll have homework, and then we're going to start doing homework more than once a week coming up here. If we can get a chapter done in a day, we'll move the homework up so that we can try to get more done here, so we can get the final exam done on time. But most of these homeworks are not going to be nearly as challenging. I can't remember if chapter 28 has any assignments in it, or has any questions in it. Let's check to see that, if that's true. It does. Hey, yeah, there's questions. No, there's not. No questions. There's no questions in the homework this week yet, but we'll get to that.
That's fine, yeah.
Let's actually look at some questions really quick. Let's see if there's any questions.
Who
we can
did
do.
Einstein's here?
Let's see what we got here. There's physics. Nothing there. Nothing there. Might have to make my own questions.
Come in, y'all.
Okay. Trying to figure out what she's talking. Oh, it's dental x-rays. Okay. Let's see, physics library. Let's look down here and see if there's any things in the special relativity section. There might not be anyway, you just might have to choose them out of the book, which I can see here.
Are there any in the book?
Looks like there aren't any built into my open math yet, so we'll choose some out of the book as we go. We'll pull some questions out of the book as we move through it. So, in fact,
There's no math in this yet. Wow.
all right, so let's go ahead and get started on our special relativity chapter. So, anyway, going back to what I was talking about, special relativity was started a long time ago because it's not necessarily a modern physics question. Relativity is actually, that only became what is called special relativity today when we started understanding things about light and how light travels. The fact that light travels at a constant speed, for example. That's when it became special relativity. When it was relativity, classical relativity, the scientists that were working with classical relativity were working with things like what happens if the person making the measurement is moving while they're making the measurement. So an example would be there are two trains that are moving along train tracks next to each other, and they're moving at different speeds. And one person on one train is measuring the speed of the person on the other train, or measuring the other train's speed relative to their train speed, not relative to the ground. And so to know things, to know everything about that situation, you have to know a lot of things. If you want to know how fast each train is going relative to the ground, which we assume is stationary, but it's actually not, then you have to know the speed of both trains. You have to know the direction of both trains. You have to know if the observers on each train are moving on the train itself. Because if the observers are moving on a train that is moving relative to the ground, then you've got all kinds of things that have to be accounted for. And relativity in those situations is actually fairly simple. You essentially just add and subtract velocities. If the velocities are going in the same direction, you add them together to get a total velocity. If the velocities of the trains are going in opposite directions, you subtract the velocities and you get their relative velocities. It's just adding and subtracting, very simple mathematics, no big deal. Lorentz figured it out and created a kinematics that works for relativity, and that's fine. But once Maxwell came along and determined that the speed of light never changes, that changed relativity when you're dealing with things that are moving close to the speed of light. Why would it change that? Well, imagine you're on one of those trains that's moving, and the light, then you've got a light on the train, and you've got a light at the train station on the ground, right? And the train is moving at 100 miles per hour east, and you're shining the light east. And there's a light at the train station that's shining east. According to normal relativity, the light that's on the train will be shining faster. In other words, the light rays will be moving faster because they're on a train that's moving 100 miles per hour. So the light on the train should be going the speed of light plus 100 miles an hour. And the light at the station should be just going the speed of light. But that's not true. Both lights will be going exactly the same speed. And that's the thing that changes. And we don't necessarily know why. There's some theories about it, but we don't really know why.
It's like the light goes through a medium, whenever it exits the medium, it goes back up to speed.
Yeah, I mean, that's true, but it's not necessarily related to what we're doing here. It is related in a kind of a roundabout way. It's related because the speed of light is always constant in a given material. It just never changes if you're in the same material. So this idea that light always moves at this constant speed, and that and additionally that this constant speed is, well, this was actually discovered by Einstein. Einstein also discovered, as he was doing the mathematics of this, that there's nothing that can go faster than the speed of light. And that's not just something that was observed. That wasn't an observed thing. That is actually something that was discovered mathematically and determined to be a theorem from the laws that we were observing. So anyway, and so what was it that made Einstein so brilliant? The thing that made Einstein so brilliant was he was the first one to accept this problem. Up until Einstein came along, every scientist in the world was trying to prove that light actually did not behave the way that Maxwell said it did. Maxwell had proven mathematically that light would always be the same speed, but everybody else was trying to prove that otherwise. They were trying to prove it wrong. And there was a famous experiment done by two scientists named no, that's not interferometer speed of light. Michelson and Morley, that's who it was, Michelson and Morley. So Michelson and Morley built this device. This is a block of granite, not a small block of granite, okay? This is a block of granite, and it's floating inside of a pool of mercury. So if you ever want to float a piece of granite in something, it floats in mercury, just in case you're wondering. So they floated this block of granite in a pool of mercury, and the reason that they did that is because it removed all the vibrations from the ground. The vibrations from the ground were absorbed in the mercury fluid. And so this block was perfectly still, just about as perfectly still as you can get on Earth, relative to the Earth's surface. And then you can see in the corners here, there are these things. These are mirrors that are, some of them are fully reflecting mirrors. Some of them are partially reflecting mirrors. And this is called an interferometer. You shine light into one of the partially reflecting mirrors, and half of the light will go straight through. Let's say that this is the partially reflecting mirror here. Half of the light goes straight through, and half of the light reflects off the mirror and turns at a 90-degree angle. So now you have two beams of light from the same light source going different directions. They're from the same exact light source, so if they come back together after traveling the same path length, if they come back together and you recombine them, they should line right up with each other and not have any problem if they follow the exact same path length. However, if their path length is slightly different, or if one of those paths is moving faster than the other path, relatively to the other path, then they would guess that one of those lights would go faster if it was moving along a path that's moving faster.
Cause dissonance.
Well, it should, yeah, if it was sound, but with light we call it interference, right? It's just what we just learned in the last chapter. Interference patterns are created by waves that overlap and have a pattern where the peaks and the troughs line up to make dark spots, right? And that's exactly what will happen if you misalign these waves. So what they did is they put this thing together, and then they rotated it so that it was pointing, so that the paths were pointing 90 degrees to the Earth's motion in its rotation and in its circle around. So the Earth rotates around the sun, but it also rotates around its own axis. Those two rotations combine for a really fast speed on the surface of the Earth. And so they rotated this thing so it was 90 degrees to that rotation, to those two rotations, and then they lined it up so that it had no interference. So they adjusted everything so it had perfectly no interference, And that means that the waves going down one path and the waves going down the other path were lining up exactly right on top of each other. And then their thought was that if they rotated one of these arms, either this one or this one, into the rotation, the direction of the rotation of the Earth, that one would then be going faster. And then it would create some interference. Right? When they did that, they saw nothing. No interference. It did nothing for them. And they did it again and again and again. And it did nothing again and again and again and again. They considered it a failed experiment, so they started to think of explanations for this. Well, this should have worked, so we're going to assume that there's a medium around the Earth that forces light to travel at a particular speed, and we call it the luminiferous ether. And it just can't go beyond a certain speed when it's in that medium. And the Earth is dragging this medium through the cosmos. They created this huge theory of things that they had no proof for, no evidence for. But they figured they'd find the evidence eventually. And Einstein came along and said, "You're ridiculous. Why don't you just believe what the theory said and go from there and see if you can prove the theory wrong?" Right? What they were doing is they were assuming the theory was wrong and trying to prove their theory, trying to create a new theory that was supposedly right, which is the way science had been done for many, many years. For many, many years, we had assumptions about science, assumptions about the way the universe worked, and we tried to prove them. And sometimes it worked out, but a lot of times it really didn't. Most of the time it didn't. And so for many, many years, many centuries, we held on to beliefs about science that we thought were true. And it wasn't really until the past couple of hundred years we started to do this other approach science in a different direction, which is believe the theory that comes from mathematics, to believe the mathematics and then try to prove that wrong. If you can prove it wrong, then you create a new theory from the mathematics. If you can't prove it wrong, you accept it. And so Einstein said, you obviously can't prove it wrong, so let's accept it and go from there. And Einstein was the only person to be able to accept this. And why was he the only one who would accept this? Because if you accept that light can only travel at one speed in a vacuum, that it only travels at one speed and it never travels any faster or any slower in a vacuum, then that suggests something about the vacuum. Two things in particular. The two things that it suggests about the vacuum is that the vacuum is not constant. If the speed of light is constant, the vacuum cannot be. In other words, space is not a constant thing. It is not something that is always the same all the time. And also, time is not what we thought it was. And that's the biggest thing that Einstein was able to see past that other people weren't, is that time is not what we think it is. Now, don't answer this question, Packer, because I talk about this all the time at dinner and in our house. It drives my wife crazy. But why is time not a constant thing that we think it is? We think of time as something that ticks along and passes by. Why do we think of it that way? Why is it something that we think of as a constant thing? That's actually a really good answer. It's not the most immediate answer because, if you think back to when time was invented, do you know who invented time? Neither do I.
Probably the Catholic Church back again. Older than that.
Much older than the Catholic Church. You go way back to prehistoric times in time to see who invented time. You go way, way back. And, people, when they were living in caves or wherever they were living, way back, they were looking for a way to figure out how to survive. How do you survive? Well, there are predators at night that are scary. It was always frightening to be out at night because humans can't discern things at night very well. So that was the time to hide, to go into a cave, to climb up into a tree, to get away from the predators, right? It was also colder at that time. So it was time to get somewhere where you could get shelter and get warm. There was a time of the year when you could find things growing and eat them. And there was a time of the year when you couldn't, and the only thing you could do was to kill things. And that was the beginning of time. Eventually that led to cycles of harvesting and growing things and hunting and preserving meats. Eventually it led to migratory patterns of people as they migrated from hunting grounds to growing grounds to other things. And it led to so many things that we have evidence for in time. And eventually, I believe it was the Egyptians that came up with the current time system that we use. Nobody really knows, but well, somebody probably has some information on this that I don't have. But I think it was the Egyptians that came up with the
They were the ones who divided the year.
hexadecadecimal system. Right? They divided the day into time increments. They also divided the year. I don't know if they did the year we
They
use.
did the year, the Arabs did the day. They
Is that
took
how it
out
went?
The 60-60-12 system is an Arabian thing.
Oh, is it? Okay, so the Egyptians did the year, the Arabs did the day, according to Packer.
As well as I remember.
Yeah, we may be wrong. We're not really sure. But people of very ancient times were trying to do this. And the second was literally determined by our heartbeat. You know, the second that passes by every second was somebody that said, my heart beats about once every, I'm going to call that a second. You know?
It's like, that's a consistent beat.
Yeah. There's also a story of an Egyptian who actually, maybe it was a Sumerian or something from way back when, thousands of years ago, who had a cracked pot. And I wonder if this is where cracked pot comes from. But anyway, had a cracked pot that was dripping water, and then decided to use that as a timepiece. And we know that timepieces were jars with holes in them were designed as timepieces. That's well known. But it's thought that started with somebody that just had a pot that cracked and noticed that it gave a regular dripping, And nowadays we have these elaborate devices that are based on a crackpot idea. I mean, and we call it time, and we assume it's something that is natural, and we assume it's something that is inevitable, and we assume that it's something tangible. But it's something that man invented. Really, because we're mortal, because we die and we live and we're scared of things, and the earth rotates on its axis, and we perceive the sun coming up and going down when really it doesn't do either of those things, right? So it's really time is an invention of man. Okay, it's not something that is part of space, part of the universe. Necessarily, not in the way that we perceive it anyway. However, time does have a place in physics, but we do need to think of it differently. We need to think of it as more related to what light is and what space is, rather than something on its own. And so Einstein was able to accept that. Einstein was able to accept that space and time were actually going to be one thing now, and not separate things. They were going to be kind of interrelated and irrevocably tied to light, and how light travels at this constant speed, so-called, which, all of a sudden seems really strange. Because what is speed a measurement of?
Time and space.
Time and space, right? And we just said that time is not what we think it is, and space is not what we think it is. So what really is what we think it is? So light is the thing that we know is constant, whereas time and space are not. So it starts to get really weird. But being able to accept that, and being able to see beyond what all humans from the beginning of time until Einstein lived, which amount to billions of people, billions of people lived and died before Einstein. And he was the first one to be able to accept this and see beyond what had been invented and developed by all humankind before him.
So if you would have figured out time differently, like based on something that's more relative, then maybe you further along in physics.
Yeah, maybe. Maybe if the first person who came along and said, I think that the distance traveled between when that sun comes up in the morning and when it hits the fur of this razor-backed saber-toothed tiger That's going to be what I'm going to call time. If they could have perceived that, well, if they could have perceived that back in caveman times, we'd probably be an interstellar species at this point.
And then we wouldn't be trying to breed razorback hogs to tigers.
That's right.
I was paying attention.
Oh man. So anyway, without a doubt, Einstein is because of this one thing that he did, and he did so much more than this, but because of this one ability that he had to see beyond what the human race had not seen, we consider Einstein to be one of the most brilliant human beings who ever lived. Maybe the most brilliant human being who ever lived, but certainly in the top 10, without a doubt. Even if you consider everybody that ever lived, and even he had his limitations, which is kind of interesting. He struggled as his theories were pushed forward into other things. He struggled to see what other people were seeing. Once he laid the groundwork, a lot of people took it forward, but he had a hard time taking it forward into, for example, quantum mechanics. Quantum mechanics is the direct result of Einstein's theories, but he couldn't see it, which is really interesting. And it had a little bit to do with his upbringing. Einstein was Jewish, and while he was not necessarily a practicing Jew, he didn't really practice Judaism very religiously. It was still part of his upbringing and very much a part of who he was, even as he was older. And he had a hard time accepting quantum mechanics because it implied that things behaved in a very statistical way, in a way that was very much like rolling the dice. And he couldn't believe that the universe was so random as he thought it. And I would agree, I don't believe the universe is random at all. But it does, you can explain it and you can model it using statistics. And so it's just a different way of looking at it. And it's much easier for us to look at it as it's been developed over the years than it was for him to look forward and see it. Looking back on it is much easier. But anyway, this changed, and Einstein did not just change, Einstein did not just change physics with his theories. He changed all of science, all of technology. He changed art, and he changed history, and he changed politics. He changed everything with this. Everything in the entire world was touched by Einstein in some way or another, and is being more and more touched by Einstein the further we go forward into time, relatively speaking. So let's talk about what Einstein did from the very beginning. It's really quite simple. Einstein made some postulates. What a postulate is essentially the groundwork that you're going to build a theory on. You have to consider laws when you're considering physics. Laws are observed phenomena that are always observed to be the same way all the time. And you have to start with laws and then build from there. If you don't build on top of laws, some kind of groundwork that you're going to assume to be true, then there's nowhere to go. Because some things are unexplainable. Some things you just can't explain without, you can't explain at all, really, without some kind of godlike knowledge. Because there's just no way to explain them. There's no explanation for them. And so you have to kind of build on these things. So the first postulate, first of all, we have to make a definition. This inertial reference frame. An inertial reference frame, the definition of an inertial reference frame, is a reference frame in which a body remains at rest, but a body that is at rest remains at rest, or a body that's in constant speed in a straight line stays in that constant speed in that straight line unless it's acted on by an external force. So that's what we call an inertial reference frame. That's the frames that we've been assuming exist in many things that we do in physics. But we have to understand that to understand his postulate. The first postulate, the first thing that Einstein is going to assume to be correct without proof, he's going to just assume it's true because proving it would be difficult, is that the laws of physics are the same and can be stated in their simplest form in all inertial frames of reference. So what he's saying here is that Newton was right. Newton's laws work in inertial reference frames. As long as you don't accelerate your reference frame, as long as you're not doing physics in an accelerated reference frame, like in an elevator that's just starting to move or something like this, or in a spinning room, as long as you're not doing your physics in those kind of situations where things are accelerating, then Newton is correct. And it's true. It is true that we've always observed this to be true. So we can accept that to be true without, balking too much at that. Then the second postulate comes from the Michelson-Morley experiment and from Maxwell's equations. And that is the speed of light c is a constant independent of the relative motion of the source. It doesn't matter if the source is moving or not moving. It doesn't matter if the observer is moving or not moving. The speed of light is going to be the same for all inertial reference frames. And that's his second postulate that he started. So those are the two things that he's building this on. One thing that they want to point out here to make sure that we remember, the speed of light is not necessarily constant in different materials. This is not what we just said in the second postulate is not the same as the speed of light is the same in all materials. If a light goes from one material to another material, it can change its speed. That's not one reference frame to another reference frame. That's just one material to another material, right? So that has nothing to do with it. Okay. So that's the starting place of relativity. Now, if you ever have somebody come to you and talk to you about how they're going to travel back in time with going the speed of light or something, because this happens all the time in science fiction and other things, this actually is going to violate one of the postulates of relativity. One of the postulates of special relativity is that physics works in every reference frame. Well, according to physics, you cannot go backwards in time. Time goes forward, right? And so that actually is something that is not allowed to happen.
But you can't go forward.
You can go forwards in time, and you can travel faster forward through time than normal, or slower forward through time than normal. But you cannot travel backwards.
That shit called
Quantum leap?
Yeah, that's it.
So, anyway. All right, so here we're going to do, we're going to look at some concepts that are affected by relativity, simultaneity being the first one. So simultaneity is the idea that two things happen at the same time. Okay? So we use this idea all the time in physics, in science, in everyday life, this idea that two things happen at the same time, right? But while we're doing it, we can easily show that it's not true in any given circumstance. Okay? For example, let me think of a good one here.
The second hand ticks down a second, and I see it tick down a second.
That's right. So, that one's, I'm looking for a more everyday kind of occurrence. For example, let's say that Scott and I awoke at the same time. We both got up at 6 a.m. We had our watches synchronized exactly. We both got up at 6 a.m. Right? And that's true. Sure, why not? It's absolutely true. Then we have somebody who's watching us from Hong Kong. Okay? Really good vision. But you're closer to Hong Kong than I am, by however much difference. So when you wake up, the light from your body getting up out of bed that reflects off your body getting out of bed is going to reach Hong Kong before the light of my body when I get out of bed. It's going to get to Hong Kong quicker. So the person in Hong Kong is going to see you get up first, and then me. But according to us, we woke simultaneously. because we're equal distance from each other, right? As I see you get up and I'm getting up, then it's simultaneous. But there's a problem there too, because I am right next to me, so when I detect myself getting up, it happens very quickly. But the detection of you getting up took time as the light traveled from you to me. Right? So technically, you got up before I did because the time that it took for you to get, for your information to get to me. The idea behind this is that information takes time to travel because it travels over a distance and it travels at the speed of light. So information that is carried by light, which is often what we're observing is light, is traveling no faster than the speed of light. It can travel as fast as the speed of light, but no faster. And so there's always going to be some kind of discrepancy in simultaneity. So here's the example they give us in the book. Here we have two observers, one on a train, one standing by the train tracks, right? Observer A, being on the train inside the train car, sees the light from the two lamps at the same time. She's directly in between them. They arrive at her at the same exact time. Because according to her frame of reference, which is an inertial frame of reference, because it's moving at a constant speed, the train's moving at a constant speed, according to the inertial frame of reference, because physics is true there as it is everywhere in an inertial frame, the light travels an equal distance to her from the front and the back of the train. She doesn't even know the train's moving. It works just fine for her. Observer B, however, notices something different. Since the train is moving to the right, this light that is on the left is behaving differently than the light is that's on the right. Right? Let's see what they're saying here, because I want to see what experiment they're trying to do. There's several experiments you can do here. So they're doing, say, so we have observer light, we have two lights. The flashes are produced, so two lamps, observer A is midway between them, observer B, the car is moving to the right. They arrange the lights so the flashes are emitted just as A passes B. So just as the observer A passes observer B, the lights flash. Okay, so that's when the lights go on. And A and B are equidistant from the lamps at that time. So they're both equidistant from them, right? Observer B is going to measure the time interval between the arrival of the light flashes. So the person down here is going to measure the time. And then, let's see. According to postulate 2, the speed of light is not affected by the motion of lamps relative to B, so the light travels equal distance at equal speeds. So observer B is going to measure the light flashes to be simultaneous. Let's see here. And then then they do this. And then we're going to see, okay, so the next thing that they're going to look at is what observer B is seeing happen to observer A. So as observer B is looking at observer A, they're going to perceive the light from the right reaching observer A before the light from the left, because observer A is moving towards the light from the light on the right. So in other words, the lady in the car, according to this person on the railroad tracks, the lady on the train is moving towards this light, and the light is moving towards her. So he actually perceives the light hitting observer A before the light on the right hitting observer A before the light on the right, but perceives the light hitting him at the same time. It starts to get really weird, doesn't it? Even though the light is traveling the same speed to him, he's observing it as if it looks like it's traveling faster to her if he knew that she was directly between them, but that's not what he actually sees.
He sees her
But it-
moving, not the light.
That's right. What he actually sees is he actually sees her moving towards the light moving towards her, and so he doesn't observe her directly between the light as she observes herself. She perceives herself as directly between the two lights. He does not. In other words, space is changing. You could think of it as that. Now, these things cannot be observed by the human eye. These are thought experiments, and Einstein, another brilliant thing that Einstein did was he created this idea of thought experiments based on mathematics, where you did what you think would happen if you could observe these things. The only way you can observe this is if the speed of the train is very close to the speed of light. And so that's why it has to be a thought experiment, because trains just can't go that fast. And we can't observe things that are moving that fast either with our eyes. And then here we consider what observer A sees happening. So this is what the lady in the train observes. She sees the light from the right arriving before the light from the left. Let's see. Since both lamps are the same distance from the reference frame, from her perspective, the right light flash occurred before the left, and a relative velocity between the observer affects whether the two events are observed to be simultaneous. So if she's on the train and she observes the lights to come at her she observes the lights to flash simultaneously, he will not observe them to be simultaneous. If he observes them to be simultaneous, she will not observe them to be simultaneous. Okay? Even though we designed them so that they should both see them simultaneously. According to her, if she sees them simultaneous, he will not. If he sees them simultaneous, she will not. And that's the problem with simultaneity, is it doesn't exist. It's relative. It's relative to the observer. It's relative to who's observing it and what their relative motion is, what their relative behaviors are. Now, how do we make sense of this? Look, going through a thought experiment is nice, but we'd like to be able to have some concrete way of calculating it so we don't screw it up. It's really easy to mix it up if you're just talking about it. So we try to make it more calculable. All right? So here's another. Here is an actual experiment that it has been done, and you can do this experiment. You can do this experiment if you're on the space station or another object that is in orbit around the Earth, because going in orbit around the Earth, you're moving rather quickly. So the idea is to build a clock that's based on travel of light. So you have a light source and two mirrors, or one mirror and a receiver. Actually, you put it through an interferometer again, so that you have multiple. You have multiple mirrors, so that it bounces many times and goes a very, very long path. But the idea is that you have this light source going through this path, and this path needs to be a fairly long path, and then eventually hits this receiver that is right back next to the light source. And the idea is then to measure to measure how much time is changing as you move very quickly. You measure how long the path gets, because the faster you're moving, the longer it takes to get through this clock, the longer the light takes to get through this clock, because it's going a longer path. And this is the reason it goes a longer path. As your time clock moves on your space station or space shuttle, whatever it is, as it moves, the light is actually traveling through space at an angle. Instead of just going straight up and down like it looks like it's going in your time, in your reference frame, you think it's going up and down in the space shuttle, but since the space shuttle is moving through space, it's actually going at an angle and traveling a longer distance. That make sense? That longer distance, of course, is going to take more quote-unquote time, if we want to think of it that way. And then this clock is then therefore going to tick slower. The tick used to be the distance, it used to be the time that it took for the light to leave the light source and come back this short distance. That used to be one tick on the clock. Tick, 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 tick. And that's how all clocks work. All clocks work by having something moving through some distance, and when it moves through that distance, you make the clock tick 1 second, right? Well, this second just got longer because of the faster time that you've traveled. Another way to think of this, which is the more classical way it's been described, is imagine that you're on a spaceship in London, and you're leaving London and you're going very close to the speed of light. And you're watching Big Ben tick away at seconds as you leave. When you're sitting there before launch, Big Ben is ticking away seconds like normal. Tick, 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 tick. And you're watching the second hand, even though Big Ben doesn't have a second hand. But you're watching the second hand tick every second. And that light from the second hand takes time to get to you because it's traveling at the speed of light. But once you start traveling at close to the speed of light away from the clock, it actually has to go a longer distance to get to you. So it actually takes longer for every tick to get to you. And the further you go, the longer it takes for every tick to get to you. And the faster you go, well, it's actually the faster you go, the longer it takes for each tick to get to you. Because the ticks have to catch up with you. Now that they're moving at the speed of light and you're moving close to the speed of light, it takes them longer to catch up to you. And so the ticks slow down, essentially. The faster you go, the more they slow down. Right? This is what we call time dilation. It means that time stretches out. Each second gets longer the faster you go. You don't see this effect when you're going at slow speeds, anything lower than about half the speed of light. When you get to going about half the speed of light, then it starts to be noticeable in the calculations. And the way that this comes from, we can do this geometrically, the time that it takes to travel along just this distance here, going up and back with the speed of light is this time, right here. We call this the proper time, delta t0. It's the distance straight up to the mirror and back, 2d divided by the speed of light. But the time that it takes to go along this path length is 2 times s, which are these hypotenuses of these triangles, which is determined by some trigonometry here. And we can see here that s is equal to square root of d squared plus l squared, where l squared l is... What? No, you're not going to reproduce this math, but we're going to use it in the end. We're going to use what the result is. So we're going to get an equation out of this in the end. So the delta t is going to be 2 times s over c, where s, 2 times s, is the velocity of the ship, or the velocity of the clock, the absorbed velocity of the time frame, times the time that it travels, that distance. And it ends up being 1 over the square root of d squared, which is the distance between your clock, plus the velocity times change in time over 2 squared. Take the square root of that whole thing. That's your distance. And that means your time starts to look like this thing, which is really messy. And then it starts to, you take the square of it to get rid of the square root, and then we do some more math. And then in the end, we take the square root again, and this is what we get. The time that elapses when something is moving close to the speed of light, which we're going to call the relative time, or they call this the time dilation, which is delta t, is equal to the proper time, which is the time that would have taken if you weren't going very fast. That would be the delta time would be 5 seconds past according to a normal clock. 5 seconds, right? Whatever it is. But then you have to divide by this square root of 1 minus the velocity of the moving object divided by the velocity of speed squared. So both of these things are squared. You take the ratio. And this 1 over this square root thing is called gamma. It's called the gamma factor, or the gamma constant. And it is something that we use all the time in relativity. This thing is the difference between time and space in relativity. So if 5 seconds go by, if your delta t naught is 5 seconds in normal time space, normal time situations, but then all of a sudden you're traveling at 0.5 the speed of light, then you put 0.5 c right here, so that you get 0.5 c squared up over here divided by c squared, so it's 0.5, and you get 1 minus 0.5 square root of 0.5, which is what's the square root of half? It's like 0.7-ish, something like that. So you get your 5 divided by 0.7. You get your 5 seconds, which is your normal time that would have elapsed, divided by 0.7, which is like 0.6. Or not 0.6, it's like 6. So you'd add a second to your time. What does this mean? This means that the 5 seconds that you that ticked by in London while you were moving away from it at half the speed of light, the 5 seconds that went by on that clock took 6 seconds in your time. The clock that you're keeping on your spaceship that's just ticking along. So you saw 5 seconds go by on Big Ben, but 6 seconds went by on your clock. In other words, time has expanded. Okay? Now, what does this mean realistically? What does this mean? Well, realistically is a bad way to say it. Okay, realistic. What does this mean realistically? This is the experiment. This is one of the experiments that was done to determine that this actually happens. Muons are a particle, a subatomic particle. They're one of the basic particles of the universe. So they're a fundamental particle. And they come from outer space all the time. They're always flying in from outer space. Muons have a very specific to say that they're flying in from outer space is true, but in this particular experiment, they're being created in the upper atmosphere. So you have a cosmic ray, which is some kind of energy ray coming in from space, from the sun or something like that. And it's going to collide with some nucleus and some atom up there in the upper atmosphere, and it's going to create a muon. Muons have a specific lifespan. They only last so long. However, when they're created in that upper atmosphere by these high energy rays, they have a tendency to be moving very quickly. They have a tendency to have a lot of energy. And so a muon created in the upper atmosphere can be going 0.950 C, almost the speed of light. They're tiny particles, so they can go pretty fast. If the muon is traveling at a constant velocity, it lives 1.52 microseconds in its own frame of reference. So if it had its own clock, its own pocket watch, it would look down at its pocket watch, and 1.52 microseconds after it was born, it would die. And what it means by what I mean by dying is it becomes something else. It actually decays into something more stable. However, if you were measuring it on Earth, you would measure something different. So let's see what we would measure on Earth. So the actual time is the proper time is the time measured in the muon's frame. It's the time measured in the moving frame. Okay? And we want to measure the time that goes by on Earth. What we observe, the time that we see going by on our clock as this muon travels through the atmosphere. So the proper time, the T0, is the time in the time frame, measured in the time frame, which is 1.52 microseconds. The V is the 0.950 times C. Remember to put that C in there, you got to have that. And we want to find delta T, which is the time dilation, or the observed time. So we go ahead and we know that delta T is equal to gamma delta T naught. Delta T naught is the 1.52 microseconds. The gamma is 1 over 1 minus V squared over C squared, where V is 0.950 C. When we plug in 0.950 C, we get 0.950 squared times C squared. The C squareds cancel, and we get just 0.950 squared, 1 minus 0.950 squared. 1 minus 0.950 squared is something like, what is 0.950 squared, whatever. It's like 0.00 something. It's some really small number. And then you take the square root of that number, and you get something a little bit bigger. And then you take 1 minus something small, and you get 3.2 in the end. Okay? So what was 1.5 microseconds now became 3.2 microseconds. Oh, sorry, that's just gamma. This becomes 3.2. Then we multiply 3.2 times our original time, which is 1.52, and we get 4.87. So the time that we have is 3.2 times bigger than the original time. Ends up being 4.87 microseconds. So as this muon is traveling through the atmosphere, it sees 1.52 microseconds of time going by. We observe 4.87 microseconds of time going by. If the muon was sitting still, how long would it live? Yes, because in its own time frame, it is sitting still, right? In its own time frame, it is sitting still, and it measured its own time. It had its own pocket watch. So in the muon's time frame, it is sitting still. That is the actual lifetime of a muon. But because it's sped up, it actually lasted longer. So another experiment that was done is that they actually created muons in an accelerator. They created muons in an accelerator, and then they put these muons, they shot them down a path that was too long for them to make it. This path was longer than the 1.52 seconds it should have taken for it to die.
Yeah, but how do you keep track of something that's wrong?
They're not that hard. Well, they are hard to detect, but they can do it. It takes. It's not about size. It's about the behavior of the particle when it encounters other things. So they have these huge detectors that all they do is detect muons. That's not all they do, but they're very good at detecting muons. And in fact, you've seen some of the material that is used for this. You ever seen a material like this when you went hunting with a bow? This is not a fiber optic, actually. This is what we call a scintillator. So you see this material in your sights on your bow. There's a coil of it, and then you're looking right down the tube of it. What this does is it collects ultraviolet light, and it collects other kinds of light as well. And it actually emits another kind of light in a different direction. So it collects it in this direction, and then it emits another kind of light. In this case, it emits an orange light. There are green ones, and there are blue ones, and other ones. But it emits an orange light along this axis. It doesn't emit along this axis. I mean, you can see a little bit of orange this way, but hardly anything. This way, you can definitely see it, right? And let me show this to our other students here. So this is just a ruler that I got from Fermilabs, just an orange see-through ruler. But you see, as you look on axis, you can see it's really bright here. And hunters use this all the time. They use it in their sights, on their bows and their guns. And it's a material called a scintillator material. It's designed specifically with it's infused with chemicals that when they absorb light, they emit along a certain axis another light. Okay, that is very similar to the materials that are used to detect muons. They use a scintillator that is designed to absorb muons one direction, and then it emits light in another direction. So when a muon hits it, it glows, and then they can detect that. So that's one way that they detect it, is using scintillator technology. In fact, this device I've got here is also another scintillator technology. It's designed to look at scintillations as well. So this is one material for that. There are lots of different ones, like I said, lots of different colors. I've got another one somewhere in here that's green. If I can find it, here's a green one. And I got these at Fermilabs where they do that kind of work. So here's the axis that doesn't glow. There's the axis that glows, and you can really see the difference if you put something that blocks ultraviolet light above it. For example, paper blocks ultraviolet light fairly well. If I put paper above it, you can see it going darker. No, not really. Let's try some thicker paper. I can see it with my naked eye here, but I can't see it on the screen very well. It's not really darkening on the screen. But it does do that. But this will collect light even in low light conditions, because it collects light from all sources, from all kinds of directions. And so that it will glow. Looks like it's glowing in the dark, and it is glowing in the dark. But it's a scintillator, and that's one of the things that they use to detect muons and other particles like this. These scintillators can be designed for many different particles depending on what they infuse the plastic with. So anyway, so this experiment had this muon going down this tunnel that was too long for it to survive. But what they discovered is that if they sped up the particle, even though the speed of the particle wasn't enough to get it through before it was supposed to die, it would still come out the tunnel, because it was living longer according to the observer's time frame. Even though the muon's lifespan according to its own time frame remained the same, the observer observed a longer life cycle for the particle. And so that experiment was one of the first experiments done to prove that time dilation is actually a thing, that time actually slows down as you go faster and faster and faster. Now, the twin paradox is one of the classic kind of examples that people give about the special theory of relativity. Although there's more than one holes you can poke in this paradox. But anyway, so the twin paradox goes like this: you have two twins born on Earth. One twin goes on an interstellar trip close to the speed of light. The other one stays at home. As the one that's at home watches her twin move away from the Earth, what happens? She sees the clock ticking, and the twin on the spaceship sees her clock ticking. But the one on the spaceship, what happens? They observe their time to just tick along normally. But the one on Earth actually observes much more time go by. Right? So if it takes them an hour to get out to Alpha Centauri and back, or whatever amount of time it takes depending on how fast they're going, let's say it takes them an hour to get to Alpha Centauri and back, going at very close to the speed of light, the people on Earth may observe years go by. And if this person was watching the clock on Earth, they would see the clock on Earth take years to go by. If they could see that clock the whole time they're going to Alpha Centauri, it would slow down, just like we said earlier with Big Bang. But her clock on the spaceship, she's observing, just ticks along normally.
Yeah, but one's perceiving it and the other one's perceiving it, right? So
This one can see that clock on Earth slowing down.
no, but they're seeing their clock. They're seeing the one on Earth is seeing their clock. So it's perception.
It is, but in the end, each one sees their own clock, and the one that's moving, just like the muon, sees their time normally, go by normally as they're moving. The one that is not sees their time go much. According to their point of view, it takes much longer for the spaceship to get out and back. So think of it this way: the light from Alpha Centauri takes years to get to Earth. Okay? And that's what you see on Earth. You see the time, you see that light taking years to get to Earth. But in the time frame of the light, almost no time goes by. Now, the reason that this is a paradox, one of the reasons it's a paradox is because it's not easy to understand. Our understanding of time doesn't allow us to make this step very easily. But essentially what's happening is the so-called stationary observer is going to get older than the one who is moving in the same amount of quote-unquote time. But it's not the same amount of time, right? There is no such thing as the same amount of time in relativity. There never is. And that's why it gets so confusing and so obnoxious. Now, one of the problems with this is that there is no such thing as a stationary observer, right? We have to assign somebody to be a stationary observer, right? So we have to decide who's going to be stationary and who's going to be moving, right? Well, so this paradox is not exactly foolproof. It is definitely faulty. So right here, the premise is faulty, and there's contradictory conclusions. The astronaut's motion is significantly different than that of the Earthbound twin. Accelerates to a high velocity and then decelerates to the new star system. Then she accelerates and decelerates on the way back. The Earthbound twin does not experience these accelerations, so it's not a symmetrical situation. So, you've got that problem. You've also got the problem, let's see, some other ones are... So the acceleration is one problem because acceleration is not allowed in special relativity. Let's see. There's other holes you can poke in this thing, but in the end, it is roughly true that when you have two objects that are in the same time frame, whether or not it's accelerating, and this was addressed in general relativity when Einstein expanded his theories to general relativity. Because the twins start off in the same time frame, we consider that one to be stationary because they start in the same one, even if it's moving. And because the rocket is moving relative to that front time frame that they were both in, to that to that original stationary time frame, then their time is the time that is going to stay. You could say stay normal. I mean, you can't really say that, but the clock inside their spaceship as they speed up towards the speed of light is going to change. And it's going to change relative to this one. This one is going to keep ticking along like it normally did, but this one's time, their seconds are essentially going to be longer. You could think of it as. So each second that ticks by in this spaceship is going to be worth many seconds on Earth. So 1 second passes by and they age 1 second, while these people age 8 seconds. So each second on the spaceship is now longer. And that's why we call it time dilation, because it stretches each second out. And that's why when they looked back towards the clock on Earth, each second looked longer. Because the clock that she was born with is now ticking slower for her. The clock that she took with her on the spaceship looks like it's ticking normally, but it is actually recording 1 second for every 8 seconds or however many are on Earth. Now, if this is confusing, that's normal. It's supposed to be confusing. We were raised, in our brains are conditioned to think of time as this constant thing, and it is just not.
So if you on Earth today, whenever a spaceship takes off, hit a stopwatch.
Where's the stopwatch?
Both of them are in person's hand. You hit a
In which
stopwatch.
hand? Whose person's hand? Like one in each person's hand?
An observer. Okay. And they hit both stopwatches. And they take one stopwatch and they throw it onto the rocket.
Yep.
Alright. So both of them started at the same time.
Both of them start at the same time in the same place, which is true for these clocks.
Goes and comes back. The one on the ship will have
Less time ticked by.
than the one on the.
Yep. So as the clock speeds up because it's on the spaceship, its time slows down. Time dilation.
Now does that work going towards and coming back from?
Yes, it does. Doesn't matter what direction you're going.
As long as you're moving faster than.
As long as you're moving close to the speed of light, it will be observed. Okay. Yeah, and there's a reason that this stuff is, we don't mess with the math of this stuff. We've done just the very simplest math possible to get to the time dilation. And that was the easiest thing that he ever did. But he also did it in 3 dimensions. Technically, he did it in 4 dimensions. But. Okay, so that's what we call time dilation. Let's take a look at,
Let's do that next time.
so what I'm going to do is I'm going to copy some questions and I'm going to put them right into the assignment here.
You're going to open the assignment, it's just going to be some instruction.
Yep, pretty much.
Okay.
So I like that. What is, let's do a what is gamma problem. Of course, we have to make sure we do the problems that they don't give you the answer for.
Gamma is a letter in Greek alphabet.
Oh, that doesn't help. Oh, I hate it when you can't copy the Greek, the math stuff.
It's all in Greek.
Let's see.
I'm with you.
That's not going to help me.
Publish this chapter before the language equivalent is
Show math as. That's not going to help me either. I want to. Let's see. What is, so let's Erase
Type out
that.
gamma.
Let's add in some code here. What is gamma? If, what did the question say? What is gamma if v equals 0.1 c? Oops. V equals 0.100 c. And then what's part B?
The other one's, 0.9.
0.9.
0.09.
V equals 0.9. Okay, so there we go. We got our first couple questions. Let's see, K neutral pi particle, pi meson, relative. Copy. Can create movement. Moves by at let's see, here we go, 0.98 c. And lives how many seconds?
1 times 20, 1.24 times 10 to the negative 8.
Good night. This is just not. Lives how long?
1.24 times 10 to the negative
1.24 times 10 times 10 to the minus 2.
negative 8.
And it rests like that.
Negative 8.
Oh, times 2 to the negative 8. Okay. All right. And look all that good. Okay, so next. Oh man, we're almost done. We're done already today. Let's go to the next one anyway.
Do what?
We're gonna do the next section really quick. How many sections are in this chapter?
A lot. 6.
So if we do this one, we're good. So length contraction. So here's another thing that is, so we have time dilation. Time gets longer the faster you move. But length does actually the opposite. For the person on the spaceship, they're seeing things coming at them, right? But the light that's coming towards them is also coming at them. So the things that are coming at, they're moving towards the thing that the light is coming towards them from. And so when they start to measure quote unquote distances, they start to see things getting shorter. Now on their spaceship, or in their own proper time frame, things don't change at all. But the universe around them gets smaller. Okay? So there's a proper length, which is the length that something is measured in the proper time frame. So if you're measuring a distance from a velocity and a time on the Earth from a non-moving observer, or an observer not moving in the time frame, or in the same time frame, for example.
Wait, so the line, I don't remember which side section is shorter. the universe just got a whole lot smaller right after we discovered travel at the speed of light is actually accurate?
Yes. So, so the proper distance is calculated using the let's see here. So the proper distance is calculated using the time, the dilated time, actually. Let's see here. So the muon that's discussed earlier, they have the observer on Earth measures a distance using the speed, which is 0.950 c, and the time that they see, which is the dilated time. So they get a proper distance of v delta t. However, in the muon's frame of reference, they observe a contracted length, which is the velocity times the proper time, the time in their time reference. So this can get a little confusing. Proper length is velocity times dilated time. Contracted length is equal to velocity times dilated, or times proper time. So the proper and the calculated are in different equations here. And that's to be expected, actually, if you think about it. But anyway, so the observer on Earth observes this muon traveling 2.01 kilometers, but the muon observed itself only moving 0.627 kilometers. So according to the muon, it traveled the right distance for the right amount of time at the speed that it was going. But according to the observer, it saw it move further. That's why that particle could get all the way through the tunnel, because it observed it moving further in a longer amount of time. All right? So really what happens is that same distance for the muon actually got shorter. Now what is the, so there's an equation for this. So here's the definition of proper length. Proper length L0 is the distance between points measured by the observer who is at rest. Remember that proper time was measured by the observer who is moving. Proper length is measured by the observer who is at rest. Okay? How does length contraction work into the math? Well, it turns out that length contraction is just the definition of velocity, essentially, in each time frame. You put them all together and you get this gamma out again. But instead of being multiplied by gamma, you divide by gamma. So it's the proper length times gamma gives you the contracted length. Oh, sorry. Proper length divided by gamma gives you the contracted length, or length contraction. So not only is the space that they travel in, but the object itself. So if you're traveling in a spaceship, your spaceship actually gets shorter too. And that actually accounts for why the observer at the train station saw the light hitting the person on the train at different times. Because what was actually happening is that the train was getting shorter. That's one of the things that was happening. So as things move faster, they actually get shorter. Space gets shorter. The spaceship gets shorter. And, depending on who the observer is, of course. If you're the observer on Earth, the spaceship looks like it's getting shorter as it's traveling. But if you're the observer on the spaceship, the distance between the Earth and Alpha Centauri, and the Earth and Alpha Centauri themselves get shorter. Right? So we've got these two things. As you're going faster, two things happen. Time ticks slower, and space gets smaller if you're the person on the spaceship, according to the person on the spaceship. According to the person on the Earth, if you're watching the spaceship go away, the actual time that you're experiencing actually goes faster. Or you could think of it as if you could see the clock of the spaceship, it's getting longer, it's ticking slower. Well, no, actually, because there's some other things that happen as well that we won't get to until we get into some other things. But what does happen is really interesting. If you go faster and faster and faster, and eventually you hit the speed of light, gamma becomes 1 minus c squared over c squared, which is 1, right? So 1 minus 1 is,
0.
square root of 0 is,
0.
so if you multiply 0, with, well, and gamma is 1 over that square root, so if you multiply gamma times your time, you're 1 over 0, and your time becomes infinite. So essentially, each second takes an infinity to pass. In other words, time stops. If you go the speed of light, time stops.
But distance becomes irrelevant. It becomes 0.
And if you go the speed of light, gamma become 1 over gamma becomes 0 instead of infinity. Now you have 0 times your length, and the entire universe becomes a single point because there's 0 distance between spots. So all of a sudden you become omniscient. You become omnipresent because you're everywhere at once if you're going the speed of light. And you can see everything all at once. Because time has stopped. You can see everything that's happening all at once.
So theoretically, you would only have to be able to get to the speed of light for the most small amount of time to be able to live forever.
If you can reach the speed of light and maintain it, yes. There are some problems that we're going to encounter as we go through this. Reaching the speed of light is not as easy as it sounds, if it sounds easy. It certainly is not easy.
But once you get there, you have an eternity to do whatever.
Yeah,
you want.
once you get there, you're good to go.
It's not 1 second anymore. That's
So let's see what the implications of this are for this particular.
So time is irrelevant. So if you take the time out of this equation and just work with the speed of light.
So when we start moving at close to the speed of light, we start using distances measured in light years because any other distance becomes too short to really be relevant. So the first thing we're going to do here is we're going to travel to Alpha Centauri. Alpha Centauri is how far is Alpha Centauri? 30 light years? Alpha Centauri is 4.3 light years away. So it's 4 years for light to travel from. For us, when we're seeing the light from Alpha Centauri, we're seeing Alpha Centauri as it was 4.3 years ago, according to our time on our Earth, right? However, if this astronaut is going to travel to Alpha Centauri at some high speed, where gamma equals 30, they're telling us gamma equals 30 for this to happen. Remember, when gamma equals 1, when gamma equals 0, rather, then you're going the speed of light. When gamma equals infinity, you're going the speed of light. Because 1 over square root of 1 minus 1 is 1 over 0, which is infinity, right? So if gamma equals infinity, then you're going the speed of light. So we're not going the speed of light. Gamma equals 30. And we want to know what is the length contraction. It's L divided by gamma, so we take the original equation. It's L naught divided by gamma. We take the original equation, solve it for L, and we get L naught divided by gamma. L naught is 4.3 light years divided by 30. We get 0.1433 light years. So according to the person on the spaceship, the distance between Earth and Alpha Centauri is only 0.1433 light years. So if that's how far they see it to be, then it's going to take them less time to get there. But of course it takes them less time to get there because their clock is ticking slower. But it doesn't. But we still observe them going at that same speed, and we still observe them taking all that time to get there. According to us, they took all 4.3 years to get there and back if they're going the speed of light, and they're not quite going, so it's taking more time than that. But according to us, it's taking them the time that we expected them to take. But according to them, it's taking them less time. So when they get back, time has passed, less time has passed for them, and more time has passed for us. That's the paradox, right? That's the problem with light travel, is that it messes up time. Now, how do you fix that? How do you travel close to the speed of light so that you can go places? Of course, if you can travel the speed of light, how long does it take you to get places? No time. Right? The closer you get to the speed of light, the less time it takes you to get places. But the more time passes the places you left, So when you get back to the places that you left, then all of a sudden, nobody's there anymore. They're all dead, right? So there's a problem with interstellar space travel. It's a one-way trip for everyone involved. You're never going to see the people who travel 4 light years away, no matter how at speed they're. If they're traveling at low light speeds, you're never going to see them again because they're going to die before they get there, and it's going to be it's going to take multiple generations to get there. But if they get going faster, close to the speed of light, you're never going to see them again because you're going to die and they're going to live. So this is the problem with interstellar space travel. You either travel slowly and you never get back, or you travel quickly and you get back and nobody's there. So how do you fix it? You fix it by altering the physics, by changing physics. And that's where Star Trek comes in. That's how Star Trek fixed this problem. Star Trek invented a new type of physics that allowed them to manipulate space and time rather than try to travel through it classically. Instead of trying to travel at the speed of light through space, they actually changed space so that they could they call it warping. They warped space so that they could move through space in a different way than actually traveling through it. And that's what they call it, the warp drive or whatever else. And if you don't think that science fiction has an effect on science, you're absolutely wrong, because people are working on warp drive technology right now, and they're making progress. They're learning how to manipulate space so that they can move particles without it affecting the time as much as the time in the space as much as it would, so that their proper time stays close to the time that they left, and that their proper space stays close to the space that they left, so that when they go out and back, things haven't changed as much as they might have changed. Now, have they made it into a spaceship yet? Absolutely not. They're doing this theoretically and with very small particles for the most part, and just with very small space situations.
Ender's Game got it right.
So I'm not as familiar with Ender's Game as I am with.
What part about it?
At the end, whenever
They have a character who travels close to the speed of light looking for a place to settle, and he keeps getting in contact with the Earth, and it keeps
getting.
Yeah, he watches he sees his older brother die when he's still a kid.
Yes. So yeah, they got it right and wrong. So yes, if you could do that, that's what would happen. But the problem is, if you could do that. The biggest problem is not the space-time thing. The biggest problem is not the fact that time's going to pass by. That's not the biggest problem with time travel, with traveling the speed of light. We're going to learn what the biggest problem is when we come back to this on Tuesday. The biggest problem with this is much different. So let's see. Actually, we're going to actually go ahead and cover this tomorrow. We're not going to do a lab tomorrow. We'll cover the rest of this tomorrow, and then we'll skip lab this week, just because I don't have a lab for relativity.
We're not going to try.
I don't have any muon particles. Sorry.
I just assumed none of us would be dying in space.
We're going to send Scott off to Alpha Centauri.
Yeah.
Hey, I'm here.
Maybe we could watch a cool time or a cool space travel movie. There's lots of cool ones out there. What's that?
Check his death to the towers. That one's got all the science.
Yeah, so much science. The improbability drive. I feel like a sofa. I know what you mean.
To be fair, on the latest spaceship, they did make a hitchhiker's Falcon Heavy, they did make a hitchhiker's
I know. Anyway, it's no, we'll probably just study the rest of this chapter tomorrow so we can try to get ahead and get things going. But we'll come back to the rest of the implications of special relativity at the end of this chapter. So we're done for today. Oh, we need to get some homework from this section.
No.
Yes, homework from this section, for sure.
We will look at it till Friday anyway.
Conceptual questions.
Such a good person. I'm going to do context.
So this is the one we're going to do. Calculate.
That's good because I can't get this question right.
I can't tell you.
All right.
You should make them like A, B, C.
I need a bigger binder
Why don't you take some of the earlier chapters out of it?
because I want to review it.
You need a bigger binder.
I give it a bigger binder. Actually, what I need is just a textbook. Wherever you go.
You can show me what I'm doing wrong on this question.
This one? You just got it right.
No, not that one. The one with this one.
There's the problem. I'm also getting it wrong.
I have not got it wrong ever. I mean, right, ever.
You were supposed to.
Well, no, it's just these two.
I can't even get the first two.
Well, this one right here, you gotta have a third left. You gotta go to 3 places.
Yeah,
Don't take it right if it's only the 2.
I'm pretty sure I just rounded this to 3 places. Let's look. See how many places I have.
I think it's like 2 correct, I think. Because I don't know. I don't know what I'm doing wrong. But on these two, I just.
Wait. I have my record like 5 places, 4 places.
Did you get 13 right?
I have everything else, but I have everything but questions 2 and 3. I just haven't looked at 3.
How do you do 13?
I'm gonna look at
Your dad told me, but he didn't tell me right.
15. You're assuming the physics teacher is wrong.
He's the one that told me how to do that one, and it's not right. Just, hey, you should stop the recording.
Yes, I should. Before everybody hears, I get things wrong sometimes.
Oh, I don't know.
All right. So the homework will be
Two polarizers, right?
all in this
So the first one-
instruction section.